Okay, let's start lecture 7.3, and basically this is going to be extending our ability to simplify radical expressions. So here we have an important theorem, and I want to outline a really important part. So if the nth root of A and the nth root of B are real numbers, that's important, and we'll see later on why that's important, then the nth root of A times the nth root of B is the nth root of their product. So just a note, in order for you to use this rule, the index of the radical signs must be the same. In other words, that value in there and that value in there have to be the same value. Later on, next week, I believe, we will be looking at complex numbers. And this does not hold if the nth root of a number is a complex number. So just keep that in mind. You don't have to worry about it right now, but I'll remind you about it later on. So let's actually use that rule to simplify some of these expressions. So over here, I'll just remind us of the rule. The nth root of A times the nth root of B is equal to the nth root of A times B. So this is example 1A. And in many cases, it's just straightforward. So the square root of 3, remember the index with the square root is 2, times the square root of 5. Their index is the same even though it's unwritten. So that's the square root of 3 times 5, which is just the square root of 15. And number B, we're going to go square root of 21 times the square root of x. Well, that's the square root of 21x. So in part, whenever you have an equal sign coming over here, notice we're going for this exercise from this side, from the left. We're given something on the left, and then we're producing what's on the right. But every time you have an equal sign, you need to also be able to go, if given something on the right, you need to produce the expression on the left. So we won't see that in this particular example 1, but we will be using that skill later on. We almost always use that skill. So here we have the cube root, or the third root, of 4 times the third root of 2. Well, that's equal to the third root of 4 times 2, which is equal to the third root of 8. But if we remember that 8 is 2 times 2 times 2, then we have the final answer to be 2. So again, remember we're using this. It's supposed to be x there. It's equal to x. And remember, this is just a quick reminder. It's not a full-on reminder. I don't like the way that x looks right there, so I'm going to change it. X to the nth. Remember, this is just a small little reminder. If you review last week's lecture, there's conditions based upon whether n is even or odd, and what you have to do with x if it's even or odd. So moving on, we've done number 3. Let's go ahead and do number C. We've done. Let's do D. So we're going to do the fourth root of 5y squared. And we're assuming, it doesn't tell you, but we're assuming that all of the numbers under the radical are positive, or at least greater than or equal to 0. They could be 0. So the fourth root of 5y squared times the fourth root of 2x cubed. So we're just applying the rule. That's the fourth root of 5y squared times 2x cubed, which is equal to the fourth root of 5 times 2, which is 10. And if you want to put your variables in alphabetical order, you can. We're going to have x cubed first, if that's the case, and y squared second. And that's the best we can do. And then 1e, we have the square root of 2 over a times the square root of b over 3. So this is equal to the square root of 2, not a, but rather 2 over a times b over 3. So that's just equal to the square root, nothing fancy here, of 2b over 3a. So that's a pretty simple rule to use, and it will come in handy. So let's go ahead and find a very similar, just as you would expect, since division is really multiplication in disguise, with the only difference being that one instance where you can multiply any number on any side by 0, you cannot divide any number by 0. 0 can be in the numerator, but not the denominator. So again, we have the same qualification. The nth root of a and the nth root of b have to be real numbers. And in this case, b can't be 0, because we're talking about division. That's the normal, customary addition. Then the nth root of a divided by b is equal to the nth root of a divided by the nth root of b. And again, you should be able to go, if you're given one side, you should be able to give me the other. And if you're given the right side, and you need to, you should be able to give me the left. Always, when there's an equal sign, there's these two directions. So example 2a. I want to find the square root of 25 over 49. But by the quotient rule, that's just, so remember, this denotes the positive branch, the positive square root. So this is going to simplify. The square root of 25, the positive square root, is 5, and the positive square root of 49 is 7. So that simplifies to 5/7. Why don't you go ahead and try to do number B? B should be pretty straightforward. As a matter of fact, again, I'll just remind you, if you want to get the most out of your time spent, and you're indeed watching these lectures, then you should pause once I've done a few of the examples and you kind of see what's going on. You should pause the video when I start a new one. Try to work out the given problem, because you certainly have it there. They're in the notes available to you. And then see if you get the right answer. And if you got the square root of x over 3, then you're doing good. We have to assume that x is greater than or equal to 0, and they don't say it up there, but we're always going to assume, sometimes they'll actually say it, but we're always going to assume that the variables have the right, don't exist in the right sets to make the problem doable given our theorems. So we're going to do 2c. So we're going to do the third root, or the cube root if you wish, of 8 over 27. Some of you can immediately give me the answer already. So that's the cube root of 8 divided by the cube root of 27. So, can I write 8 as some number cubed? Indeed I can. 8 is 2 cubed. Can I write 27 as some number cubed? Indeed I can. 27 is 3 cubed. So the answer is 2/3. And our last one, 2d. The fourth root of 3 divided by 16 y to the fourth. Now normally you would consider simplifying what's under the radical. But 3 and 16 do not share any common factors, so there's nothing I can do to reduce or transform the radical, the number under the radical. So I'm just going to apply the quotient rule. So that's the fourth root of 3. And if you're thinking that can't be simplified any further, you're exactly right. And this is the fourth root of 16y to the fourth. Well, as stated, we can't do anything with the numerator, but I can write using the power of a product rule. I'll just do this in steps. 16 is equal to 4. Sorry, not equal to 4, but rather 2 to the fourth times y to the fourth. So that's going to be equal to the fourth root of 3 divided by the fourth root. Now I'm using the power of a product rule of 2 times y to the fourth power. And if you understand and you saw way back here the final answer, you don't have to go through all of these steps. But all of these steps helps you see and derive things. If you don't see it, you can try it. And I did not, and let me be quiet and write here, use exactly what I just discovered. So the fourth root of some number raised to the fourth is 2 times y, and that has to be in the absolute value. So if y is already assumed to be positive, then we don't have to put the absolute value here. I'm just being really technical. I'm using what we just learned in our last lecture. So the end result is the fourth root of 3. Since 2 is already positive, this is 2 times the absolute value of y. Why did we have to do that? Because our index is even. And that means I have to take the absolute value of 2 times y. And 2 itself is already positive, so I can bring that out from underneath or from behind the absolute value sign and just leave it on y. I have a feeling the book just gives you this as an answer, which is aggravating because that is only correct if we assume at the very beginning that y is greater than 0. And they don't assume that. But that's okay. When you're doing my math lab homework, you just got to be sensitive to what they're asking. And I'll be honest with you, if you're having problems trying to see what format your My Math Lab homework wants you to put it in, either stop what you're doing if you're getting aggravated and email me. Never let your aggravation get to the point where you're ready to bust. I hope you know by now that I'm fine that you email me with anything, and I will give any complaint a reasonable hearing. But if you are an independent worker, and I appreciate those who are, that will take you a long way in life, look at your ebook. Open up your freaking ebook and go to the section and look at the examples they're giving you and look at the final answer they're stopping at. That's going to be the same type of answer they're expecting in my math lab. So now we're just asked to simplify this. Okay. So what we want to do in the following is this. If we have a number, for example, let's look at 50. And let's do its factor tree. Well, 50 clearly is divisible by 2. And 50 divided by 2 is 25. So now 25 is clearly divisible by 5 because it ends by 5. So there are all of the prime factors. So literally 50 is equal to 2 times 5 squared. So that's what we're going to use. We're going to combine our two rules and the factorization of a given number to simplify these. So this is example 3a. So the square root of 50 is equal to the square root. Well, I've done my factor tree, and this is the format I want it. The factor tree gives me the factors, but this is the format I want, is the square root of 2 times 5 squared. Well, now I'm using the reverse of my first rule, which is called the product rule. So that's equal to the square root of 2 times the square root of 5 squared. In other words, I've been given what's on the right-hand side, and now I'm going to the left-hand side. So that's equal to the square root of 2, and since the index here is 2, that is 5. And normally we do not write it this way. We treat the radical just like it were a variable and put it on the right and the whole number on the left. And that is our final answer. Now let's do B. 3B. So the first thing we want to do is do a factor tree of 24. If it's even, I always divide by 2, and 24 divided by 2 is 12. And 12 is divisible by 2, and that's 6. And 6 divided by 2 is 3. So 24 is equal to 2 cubed times 3. But what I want to do here is notice that my exponent, so let's come over here really fast. So this is my prime factorization. So what we want to do is any odd exponent greater than 1. So this only applies to odd exponents greater than 1. For example, 3, 5, 7, etc. So let's look at my factorization right here. That's 2 to the third times 3. What I want to do is I want to write 2 to the third is 2 times my odd exponent minus 1. And then that's 2 to the 1. Remember, I add exponents. So if I subtract 1 from 2, then I have to add another factor of 2 to make up with it, and then times 3. So I want to write my factorization as this way. You can leave it as 2 times 3 if you want, but since both of these, neither of these are the same number, you might as well do it that way. So we have the square root. Let me bring it down here. Oh, crap. Let's do the square root first, and this is going to be, I'm going to do the square root first, and then I'm going to go back and I'm going to do the cube root. I wasn't paying attention to my index. So remember, this is not 3b, this is 3 star b. So let's do the square root of 24. So this only works, this little rule that I just gave you works for even indices. Well, that's equal to the square root of 2 squared times 6. So that's going to be equal to the square root of 2 squared times the square root of 6. So that's going to give me 2 times the square root of 6. So now let's actually do the real 3b, and we'll use this factorization right here. I did not notice, talking too much, that we're actually wanting to find the cube root of 24. So the underlying pattern here is you always do the prime factorization of the number. Well, here I want to note that this is a cube root. So that's 2 to the third times 3. All of that's under the radical. So that's cube root. So that's the cube root of 2 to the 3 times the cube root of 3. So that the cube root of 2 cubed is 2 times the cube root of 3. C. Now let's do the square root of 26. So let's do the factor tree for 26. 26 is divisible by 2 and 13. 2 is prime and 13 is prime. So the prime factorizations is 2 times 13. So if no even powers of any primes appear, the conclusion is the following: no simplification. So this is when index is even. So what that tells me is there is nothing that can be done to simplify this. It is completely simplified as is. So now let's do 3D. And now our index is even. So this may come into play over here. I don't know. Let's just look at it as it comes. The fourth root of 32. So we need to do the factor tree for 32. So 32, it's even, so I'm going to divide it by 2. 32 divided by 2 is 16. Well, 16 is even, so I'm going to divide it by 2. Well, 16 divided by 2 is 8. 8 is even, so I'm going to divide it by 2. 8 divided by 2 is 4. 4 is even, so I'm going to divide it by 2. And 4 divided by 2 is 2. And these are all of my primes. They're all 2's. How many 2's do I have there? 1, 2, 3, 4, 5. So 32 is equal to 2 to the 5th. And this is the 4th root. So what I want to do is I want to write this as 2 to the 5th. And I'm going to use the trick that I started to do for B. If I need to subtract 1 from 5, so that gives me 2 to the 4th times 2. And now I'm going to go ahead and I can use, that's the 4th root of 2 to the 4th times the 4th root of 2. And the 4th root of 2 to the 4th is 2 times the 4th root of 2. And that's our final answer there. So basically, what you do is when you get you look at the index of a number, of a radical, and when you do the prime factorization, you actually look at ways you can transform something into a 4th power. And here, 2 to the 5th is 2 to the 4th times 2. And there I have my 4th power, and that's what I need there. If, for example, it were instead, it'll be worth looking at this. Suppose I wanted to look at the 4th root of 3 to the 13th. Well, notice that 4 times 3 is equal to 12. So I would transform this is the 4th root of 3 to the 12th times 3. And then I'm going to transform 3 to the 12th is the 4th root of 3 cubed to the 4th power times 3. And now I can simplify. So the 4th root of 3 cubed to the 4th times the 4th root of 3 becomes 3 cubed times the 4th root of 3, which gives me 27 times the 4th root of 3. So that was just one I just made up. We'll be seeing, I'm pretty sure we'll be seeing similar things later on. Oh, we have another rule. Okay, and here is the rule, pretty much what I'm going for. So when is a radical simplified? In general, we say a radical of index n is simplified when all factors of the radicand, which is the expression under the radical, raised to the nth power have been removed from inside the radical sign. So here is literally something you need to really helpful. This list right here. Perfect squares. 1 squared, 2 squared, 3 squared is 9, 4 squared is 16. You need to know all of the perfect squares all the way up to 12. So if you know your times tables all the way up to 12, you already know these. Because 12 times 12 is 144, 11 times 11 is 121, 10 times 10 is 100. Perfect cubes. You should know your perfect cubes all the way to 5. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. And really your perfect 4 powers aren't that difficult. You actually already know them. Go up here And since 4 is a perfect square, then 4 cubed is the same as 2 to the 4th. What else do we have? 4, do I have a 9? Yeah, there's a 9. So 9 squared is the same as 3 squared squared. So that's 3 to the 4th, which is 81. And the only one you have to learn is that 4 to the 4th power is 256. I literally have mine right here as a reminder. And you should make that little list too. It will make your life simpler. So we're going to use the product rule to simplify. And we're going to use the product rule where we're being given what's on the right of the product rule, and we're going to go to the left. That's our simplification. So this is example 4a. So we're going to do the square root of 25x squared. So that's the same as the square root of 25 times the square root of x squared. Well, the square root of 25 is the positive root, so that's 5, and the square root of x squared is the absolute value of x. I haven't looked to see what my math lab, what the textbook actually gives for that problem. I think I would write them and complain if they did literally not put the absolute value sign there. 4b. Let's look at the third root of 54 x to the 6th y to the 8th. So what we're going to do before I even begin, I'm going to do the factor tree for 54. So 54 divided by 2 is equal to 27. It's 27 plus 27, 415. 27 is not even, but is clearly divisible by 3, right? That's 3 times 9. And 9 is divisible by 3. That's 3 times 3. So here are my prime factors. So 54 is equal to 2 times how many 3's? 3 to the 3rd power. But I'm not done. I actually want to do some more stuff. I want to do the same thing with x to the 6th. 6, not that big. It's 2. And let me turn it on. There it is. So here is my power, and here is my index. So I'm going to divide 6 divided by 3, and that gives me 2. So that implies 6 is equal to 3 times 2. So I'm going to write x to the 6th as x squared cubed, because I'm looking for it to be a power of 3. And 8, well, y to the 8th is equal to y to the 6th times y squared. And y to the 6th is equal to y squared times raised to the 3rd power times y squared. So that's how I'm going to transform rather. 56 is going to be written as 2 times 3 cubed. x to the 6th is going to be written as x squared to the 3rd power. And y to the 8th is going to be written as y squared to the 3rd power times y squared. And my next move is I'm going to group together all of my elements that are raised to the 3rd power. And I'm going to use the power of a product rule that says a times b to the nth power is equal to a to the nth times b to the nth. So in particular, ABC to the 3rd power is equal to a to the 3rd power, b to the 3rd power, and c to the 3rd power. So I have something like this, and I want to get it into this shape. So this again, why am I looking at the 3rd power? It's governed by the index. So this is 3 times x squared, just looking at what I have here in the blue, times y squared, all raised to the 3rd power, times 2 times y squared. So now I'm going to use the rule that allows me to split them up. So this is 3x squared y squared cubed times the 3rd root of what I have left, 2y squared. So here I'm able to simplify this right here. The cube root of something cubed is just that something, and that something is 3x squared y squared, and this cannot be further simplified, so that's times the cube root of 2y squared. Okay, not so bad. You just got to think and see the big picture clearly. Just a quick review. When we looked at this, the first thing I noted is, okay, my index is 3. So when I've got to always factor my whole number. And of course, you're going to be looking for anything raised to the 3rd power. Anything greater than a 3rd power, then you subtract or do whatever you need to divide. And so you can raise it as a 3rd power. And that's exactly what I did to x raised to the 6th power. I divided it by 3, so I was able to express x to the 6th is x squared times 3. And x to the 8th, well, I still wanted some 3rd power in there, so 6 is the closest number less than 8, which is evenly divisible by 3. So I wrote y to the 8th is y to the 6th times y squared, and then simplified there. And then I came over here and I put it all together. So this is a really, really good example to study. So actually what I'm doing right here is I kind of made it smaller in case you want to like pause it right here, look at everything I have, see it all in your notes, because this is a really, really paradigm example. Okay. So let's do C. This is example 4C. I have the 4th root of 81 z to the 11th. So we have to factor 81. Well, 81 is clearly divisible by 9 and 9. And each 9 is divisible by 3 and 3. And 3 are prime. So 81 is equal to 3 to the 4th power. How nice, right? Because that's the power I'm looking for because it's determined by my index. Now what do I do with my z to the 11th? Well, I have to find, let me write that a little bit better. They scooted together too much. Z to the 11th. So what I have to do is I want to write this. What is the closest number less than 11 that is easily divisible by 4? Well, 10 is not divisible by 4, 9 is not divisible by 4, but 8 is. So I'm going to write this as z to the 8th times z cubed. So 8 plus 3 is 11. And now I know that 8 is divisible by 4. So 8 divided by 4 is equal to 2. So I'm going to write z to the 8th is z squared to the 4th power times z cubed. So with that in mind, I'm going to rewrite 81 is 3 to the 4th power, and z to the 11th is z squared to the 4th power times z cubed. And then I'm going to use the trick. Again, we're concentrating on the factors that are raised to the 4th power, which are those two factors that I underlined in blue. So that's the same as 3z squared together raised to the 4th power times z cubed. So now I'm going to split these up using the product rule. That's the 4th root of 3z squared raised to the 4th power times the 4th root of z cubed. So now I'm able to simplify this. This is equal to 3z squared. And I don't have to worry about any absolute values on the z squared because any number squared is always positive. Times the 4th root. So normally what we do is they don't write the times. They will write this as kind of like a coefficient, and it's kind of like they're pretending that the 4th root of z cubed is a variable term. Of course it isn't, but what I mean by that is they like to keep it on the right. So 3z squared times the 4th root of z to the 4th. Okay. So we're going to be doing the same thing, but using the quotient rule. This is example 5. So we're going to be looking at the square root of 20 divided by the square root of 5. Now 5 is prime. I can't do anything with that. But before we do anything, let's apply the quotient rule. That's the square root of 20 divided by 5. Okay, well that's something because I don't need to do any factorizations here. I mean, I could have if I wanted to. But 20 divided by 5 actually turns out to be, I can simplify this fraction, and 20 divided by 5 is 4. And the square root of 4 is equal to 2. So that one wasn't so bad. Now, if you wanted to go over here and find the factorization of 20, you'll find 20 is equal to 2 squared times 5. You could do it that way. So that's the square root of 2 squared times 5 over the square root of 5. Well, that's the square root of 2 squared times the square root of 5 over the square root of 5. And the square root of 2 squared is 2 times the square root of 5 over the square root of 5. And those factors cancel out. The square root of 5 and the square root of 5 cancel out, and I get the exact same number. I think this method turned out to be easier, but it may not always be the easiest way. It's kind of good to know that you can do it both ways. So now we're looking at the square root of 50x divided by 2 times the square root of 2. Well, this is the same thing as 1/2 times the square root of 50x divided by the square root of 2. So I should not have to justify that move right now. And if you're not up to speed to understand how I got from here to here, you need to get there. So now I'm going to use the quotient rule on what's in parentheses here. And that's going to turn out to be just nice. Because all I'm doing now, I'm coming down here and simplifying. I have 1/2 times the square root of 50x divided by 2 is 25x. So now literally all I have to do is simplify what's in parentheses. So that's in parentheses the square root of 25 times the square root of x. So that's 1/2. The square root of 25 is 5, and the square root of x cannot be simplified. So our final answer is 5/2 times the square root of x. Oh, I have one more to do. It's 5c. So I have 7. So that's just, it's just a natural number times the cube root of 48 x to the 4th y to the 8th over the cube root of 6y squared. So in this case, I think it's going to be easier. So remember that's 7 times this. If you need, you can put a 7 over 1 to make it a fraction. So that's 7 times, now I'm using the quotient rule, and our index is 2. That may come into play. 48 x to the 4th y to the 8th divided by 6y squared. So I can definitely simplify this expression under the radical. So let's do it. So coming down here, that's 7. So looking over here, 48 divided by 6 is equal to 8. X to the 4th can't be simplified because there's nothing underneath to divide it, but y to the 8th divided by y squared is equal to y to the 8 minus 2 power, that's equal to y to the 6th. And my index is 3. I should have written my index there. It's important I need my index. So this is equivalent to the cube root of, so putting all this together, 48 divided by 6 is 8, and this stuff right here just came from me talking, came from over here, the simplification of the whole entire thing. So this is the same as 8 times x to the 4th y to the 6th. So 48x to the 4th y to the 8th divided by 6y squared is equal to 8x to the 4th y to the 6th. So what do I want to do? I want to write 6 as a multiple of 3. Well, that's easy. 6 divided by 3 is equal to 2. So that's going to be useful. But what about 4? Well, the closest number less than 4 that is divisible by 3 is 3. So x to the 4th is equal to x cubed times x. So that's how I'm going to write things. So all of this, remember, is multiplied by 7. Third root, or the cubed root of 8. Let's do the factor tree for 8. Eight is 2 cubed. 2 cubed. Now let's do x to the 4th is x to the 3rd times x. I'm going to put x to the 3rd right there next to the cube, and I'll add the x at the end. And y to the 6th is y squared cubed. And I can't forget this factor of x right there. Moving on. This is going to give me 7. You don't have to put the parentheses here. It's understood. So all of these right here are my bases raised to the power of 3. So I'm going to write 2xy squared, and that's going to be raised to the 3rd power times x. So I'm almost there. So this is 7 times the cube root of 2xy squared cubed times the cube root of x. Really close now. One more step and we're there. So this is equal to 7, and the cube root of something raised to the 3rd power, and it's odd now, so we don't have to, our power is odd, so we don't have to worry about any absolute values. The index is odd, so that's times 2xy squared, and there's nothing I can do with the cube root of x, but I can simplify this, because this is 7 times 2xy squared, which is 14xy squared times the cube root of x. And that is our final answer right here. Final answer. Okay, so now we're going to switch gears a little bit. And I really do not understand why this is here, but it is. They threw it into Chapter 7 for some odd reason, so we have to present it in Chapter 7. So literally, we have to go back to being in the rectangular coordinate system. And what we want to know is, suppose I have a point right here and a point right down here. I don't know how to draw a line segment. Oh, I know how to draw a line segment right there. Well, now that I know how to draw the line segment, let me draw what I wanted to draw to begin with. So, line segment. So I have the point A, and I have the point B, and this is a line segment. It's symbolized by the letter F. And it actually tells you the length right here. So I actually want to find the length of the line segment. So how do we do this? We use the Pythagorean theorem. So let me explain to you and go back and remind you something that you've known about the entire life. So I love this theorem in particular because it is amazing that the evidence is absolutely clear that this theorem was known since at least 3,000 years BCE. That's 5,000 plus years ago. So if you're given a right triangle, let me see if I can draw a right triangle for you. So if I'm giving a right triangle, how do I know it's a right triangle? We will denote it by that little bitty box right there. And suppose our sides, so if you remember from school, you have two legs, A and B, and the side opposite the 90-degree angle is C. So if you're given a right triangle, then you know A squared plus B squared is equal to C squared. This has been known for ages, and it's a very interesting historical study. You can literally, there's a history of math. The cult of the Pythagoreans in Greek are themselves an interesting cult. We use the word cult in studies of antiquity, not like it's used these days. It doesn't necessarily have some negative connotation. It's always had the meaning that it has, and in the 20th century or so, it took a negative connotation. So I want to find the length of F. So what I want to do is, did I do line segment? I want to draw a line segment. I could remember how to do it. I'm going to draw my line segment, starting here and going straight down. I'm going to erase that. Then I'm going to draw another line segment, starting right there at D, going over here. So if I know the distance of G, let me center this for you and make it bigger. So if I know the distance of G and the distance of H, then I can square them, add them together, take the square root, and I'll have the distance of F. So that's precisely what we're doing. So how to find the distance between A? Well, I subtract the y value here from the y value here. So if this is x2, y2, and this is I'm just going to give you the formula because I want to write so badly on this. So let me just go over something I can write on. So back here, I've got a right triangle, and I can't point with my mind. So suppose I'm given this point here, and it has coordinate x2, y2. And this point down here has coordinate x1, y1. How do I find the distance of A? Well, the distance of A is I just subtract the y2 value up there. Since this is a horizontal line, the coordinate right here will be the same y2. We'll have a different x, but I don't care. So sorry, that should have been y1. So if A is y2 minus y1, and how do I find the distance of B? The exact same way. I take the distance of the absolute value of x2 in this case minus y. Actually, what you would probably want to do is just take the absolute values. So that's the difference. So A squared is going to be, remember this is a positive number, is going to be y2 minus y1 squared. And I don't have to worry about the absolute value signs, because if this is either positive or negative, and when I square it, it's going to give me my positive. And B squared is going to be x2 minus, not y, but rather x1 squared. So C squared is equal to A squared. Let me just write this out for you. I actually usually don't derive this in class because I never have the room. And with this electronic drawing space, which I absolutely have every intention of using, even when we go back to the classroom, well, C squared is y squared minus y2 minus y1 squared plus x2 minus x1 squared. So if I want to find the positive value of C, I take the square root of both sides. So the positive value of C is y2 minus y1 squared plus x2 minus x1 squared. So notice here that since this is plus, I could also write the distance between 2 points as follows. Remember, C is the distance between those 2 points. This point and this point. So I could also write it, the formula, this way. C, and the reason I'm telling you this is because it's going to be the formula you see, is x2 minus x1 squared plus y2 minus y1 squared. Why? Because underneath the radical I'm just adding, and a plus b is the same as b plus a. So I just use the commutative property. So now let's go back to the actual formula. So the distance d between 2 points, and we're just going to label those points x1 and y1, and x2 and y2, and the xy plane, which is also called the rectangular coordinate plane or the Cartesian plane, is given by the square root of the difference between x1 and x2 squared plus y2 and y1 squared. Here's a challenge question, but there's enough on our plate right now. You can look at it. It's a really simple challenge question. So let's use that formula, and right here is my formula. Actually, I'll write it exactly as it is up here. So my formula is let, can I just say let? I was thinking about labeling the points. That's the reason the P became. Let x1, y1, and x2, y2 be 2 points. Then the distance d between the points, so the distance is going to be always a positive number or 0, then the distance d between the points is given by, here's the formula, d is equal to square root x2 minus x1 squared plus y2 minus y1 squared. And the thing I want to point out to you right now that I always do when you're given a formula, that minus sign right there and that minus sign right there are inherent to the formula. So if x1 or y1 are negative, they have to bring their negative sign with them. They can't use that one. And we're going to see that right now when we're going to find the distance between the point points 2 and minus 5 and 1 and minus 4. So here you get a choice. You can label the first one x1, y1, and the second one x2, y2. Or you could have labeled the first one x2, y2, and the second one x1, y2. It doesn't matter. It'll never make a difference. So let's now just use the formula. The distance is equal to x1, which is 2, minus x1 minus x2. Let me do it. Sorry. It doesn't matter. But I have x2 minus x1 instead of x1 minus x2. It doesn't really matter. So let's do it. x2 is 1 minus x1, which is 2. I'm going to square that. Plus now y2, which is minus 4, and y1 is minus 5. It has to bring its negative with it. So let's simplify this. 1 minus 2 is minus 1, and that's squared. 4 minus a minus 5, minus 4 minus a minus 5 is minus 4 plus 5, so that's squared. So this is equal to minus 1 squared is 1, minus 4 plus 5 is 1, and 1 squared is 1. So the answer is the distance is the square root of 2. So just so you can see this and you understand what's going on, let's go over here. I'm going to erase everything. So I'm going to put in the points, 2 and minus 5, and then the point 1 and minus 4. Where did it go? 2 and minus 5. Oh, here they are. There they are down there. So this is the point. B is the point 2 minus 5. And C is the point 1 and minus 4. So the distance we're finding here, I wanted to do line segment. The distance we're finding here get rid of D. Let's turn it off. I just have to, once I guess you initiate a command, there's no way to turn it off. Sorry, people. I just wanted you to see this. So the distance that we're looking for, not line, but line segment, is that distance that I just drew right here that corresponds to H. So you need to be able to see, so this is my point 1 minus 4, this is my point 2 minus 5, and this line segment H is the distance that I just calculated, and it's the square root of 2. So yet another odd inclusion for this is the midpoint of a line segment. So let's go back over here and let's look at this line segment right here. So the midpoint will be a point along this line. So it's a point. It's going to have two coordinates such that the distance between here and here is the same. So let me actually draw that for you. It's much better if I can draw. So I'm just going to draw any old line segment. It doesn't have to be so what I'm looking for is some point right there. Maybe I should have done that on a different. So this is a point right there where, and I know it doesn't draw perfectly straight lines. This is for people who are artists. It was never intended to be for, I don't think, people teaching a math class because of COVID-19 physical distancing requirements. So this is my point. So this is my line segment. You're going to have some point here, and that's going to be x1, y1. And you're going to have some other point down here. I'll call that BR, point R. And it's going to have some coordinate x2, y2. And what you're trying to find is the midpoint. We're trying to find the coordinates x3 and y3 of the midpoint. And what makes this point special is that the distance between P and M, which I will indicate as D1, is exactly the same as the distance between M and R, which I will label as D2. So D1 is equal to D2, and the distance between D1 and D2 is the distance. So the sum of D1 plus D2 is the distance between the point P and M. So that's just conceptually what we're talking about. I'm just going to give you a formula. So here is the formula. This is really easy. So I've already given it to you here. So let x1 and y1 and x2 and y2 be 2 points with those coordinates. Then the point given by, so notice this is a point. It has an x coordinate and a y coordinate. It's an ordered pair. There's the comma in between them. The midpoint is found by adding up the x coordinates and dividing by 2. That's our first coordinate, comma, then we add up the y coordinates and we divide by 2. So let's not belabor this, let's just do this exercise. So let's find the midpoint between these 2 points. So I have one point, which is minus 3 and 3, and the other point is 1 and 0. So if I draw a line between those 2 points, and we'll do it here in just a second, then I want to find the other point that is equidistant between the two. So I'm going to call this x1, y1. I'm going to call this x2, x2, and y2. It doesn't matter which one. So the midpoint, I'm going to call that m, is given by taking x1 plus x2 and dividing it by 2, comma, y1 plus y2 and dividing it by 2. So let's do that. That's equal to x1 plus x2 minus 3 plus 1 divided by 2. y1 plus y2, 3 plus 0 divided by 2. And that's going to give me minus 3 plus 1 is minus 2. Minus 2 divided by 2 is minus 1. And 3 plus 0 is 3. Divided by 2 is 3/2. So that's our midpoint. So let's just, last thing we're going to do is see what that looks like here. Erase everything, erase, erase. So let's first draw our points. Our point was minus 3, comma 3. And our next point was 1, comma 0. So let me zoom out so we can see these. Did not want to do that. I'll just erase it. And turn on my A. Turn on. So there is my 2 points. So I'm going to draw a line segment between them. So now I want to know the midpoint. We're going to suspect it to be right around in here. So let's see. We computed it to be minus 1 and 3/2. And right there it is, pretty much where we thought it was going to be. So that's it for lecture 7.3. Yeah, that's it for lecture 7.3.